Today we're going to be talking about regular polygons, and we're going to be discussing some of the properties of regular polygons, along with talking about the activity that you did yesterday for homework, where you had to triangulate the polygons and find the total degrees in each one, or the total angle measure. So just be ready to flip back and forth between those pages in your notes, between these slides and the activity from last night. So first of all, some things that you should remember. The triangle sum theorem, you learned this way back when, but just keep in mind the sum of the angles in a triangle always 180 degrees. Okay, so every triangle has 180 degrees. And if you did the activity last night, you probably saw why that was an important fact for you to remember. And then the other thing I want you to remember is the names of the polygons based on how many sides they have. I'm going to go ahead and fill in this table and then give you a minute to copy them down. And if there are any of these that you're not readily familiar with, I would make sure that you're spending some time studying these in the next couple of days. Of course, a three-sided figure is called a triangle. We just finished talking about these. All four-sided figures are called quadrilaterals. And then remember, there's all sorts of different kinds of quadrilaterals. A five-sided figure is called a pentagon. A six-sided figure is called a hexagon. This one you might not be so familiar with, but a seven-sided figure is called a heptagon. 8 sides, of course, is an octagon. Most people know the octagon. 9 sides is a nonagon. That's another one that's a little less common, but a nonagon has 9 sides. And a decagon has 10 sides. There's not going to be any point where I ask you this like in a vocabulary quiz type format. You know, I'm not going to say, what's a three-sided figure called? What's a four-sided figure called? But there will be questions that you have to answer where I say, suppose you have a regular pentagon. You're going to need to be able to read that question and know that that shape has 5 sides. So make sure that you're familiar with these names, these from 3 through 10. These are really the big key ones that you have to remember. There are shapes beyond a decagon with more than 10 sides. A couple of them have their own names, but typically from 10 sides and up, we just throw the number out there and tack a gon onto the end. So like a 13-sided figure we would call a 13-gon, like that. Okay, a 22-sided figure we would say a 22-gon. No one ever said mathematicians were creative. So I'm going to give you a second to make sure you have that table copied down. Before we go on to the next slide, I do want to discuss some of the things that you should have found in your activity last night. So you may want to flip to that at this time. And then the things that I'm writing down here, you could just, copy in somewhere in the margins of that page or on the back of that page or something like that. So last night I gave you a bunch of different shapes. So for example, a hexagon, 6 sides. And I asked you to triangulate that. Now first, I guess I should mention this has 6 sides. Hexagon, 6 sides. And then if I had asked you to triangulate that, you would pick one corner and draw in all the diagonals that you could from that corner, sort of that seashell thing. And you end up with, when you do that, 1, 2, 3, 4 triangles. And of course, every triangle is 180 degrees. That's why that piece was important. Okay, so to figure out the total number of degrees here, I would do 4 times 180. Let's see, for that one I would get 720 degrees. So any hexagon that I give you, would always have a total angle, the sum of the angles in that hexagon would always be 720 degrees. Okay, just like in a triangle, we always know that there's 180 degrees total. In a hexagon, now we know there's 720 degrees total. Okay, if I gave you, I'm going to test my limits of my artwork here. Oh, I'm just making this shape up as I go. So this one has 1, 2, 3, 4, 5, 6 sides also. No, I don't want to do another one with 6 sides. Let's see. We make up something different. So this one has 5 sides. When I triangulate that, I can't draw this one in because there's already a line there, so that doesn't count as a diagonal. But I can go up to this corner, go down to this corner, and then I can't draw this one in because, again, there's already a line there. So that leaves me with 1, 2, 3 triangles. And then to find my total angle measure, I would say 180, 180, 180. And I would do 3 times 180 to get 540 degrees. So it seems like you could follow this pattern for any shape if you had a way to figure out easily, without drawing it, how to get from the number of sides to the number of triangles. Number of sides, number of triangles. We'll take a look at the table that you filled in when you did this for the 7 different shapes that were on that activity. And you should see a pattern. You should see a relationship between the number of sides and the number of triangles. Do you see it? What you should be seeing is that there's always 2 less triangles. Not being very grammatically correct here, but there's 2 less triangles than sides. Okay? 2 fewer triangles than there are sides. So 6 sides made 4 triangles, because 6 minus 2 is 4. 5 sides made 3 triangles, because 5 minus 2 is 3. So if you had an 18-sided figure, you would make 16 triangles. You're always making 2 less than the number of sides. Well, in geometry, we end up using n for the number of sides quite a bit. So the number of triangles would always be n minus 2. Okay, so the number of triangles is always n minus 2. If you have n sides, you have n minus 2 triangles. And then, to get the total number of degrees, we take the number of triangles and multiply by 180, because there's 180 degrees in every triangle. So to get the total angle measurement, and I guess I should be using more specific wording, the sum of the angle measurement would be that n minus 2, because that tells you how many triangles you have, times 180. Okay? At that point, I'm going to jump back to our slides. So the Polygon Sum Theorem, we're just going to formalize exactly what we just said. The sum of the angles in a convex polygon, and this can be regular or not regular, and we'll talk about the difference between the two in just a minute, but any polygon, the sum of the angles is always given by the formula S equals n minus 2 times 180. So think about what we just said. That n minus 2 tells you the number of triangles you can make in that polygon. You can always make 2 less than the number of sides, and then you just take the number of triangles and multiply by 180. So let's do some examples of that. Find the number of degrees in a 5-sided figure. So I want the sum of all of the angles in any 5-sided figure. Well, to do that, 5 is going to be my n, because that's the number of sides. So I would do 5 minus 2 times 180. Now, if you're going to type this into a calculator, make sure that you put that 5 minus 2 in parentheses, or better yet, just use your brain. 5 minus 2 is 3, so then type in 3 times 180. 3 times 180, let's say that's going to be 300, and 240, so that's going to be 540 degrees. Oh, I just did that as my example. So that means any 5-sided figure will always have 540 degrees total. Just like with triangles, we can say that any triangle has 180 degrees total. Okay, this is what I'm talking about when I said this is why you're going to have to know the vocabulary. This question says find the sum of the angles in a convex octagon. To do what we just did, you have to know how many sides an octagon has. An octagon hopefully is pretty easy. That would be 8 sides. So to get the sum, I would do 8 minus 2 times 180. Well, 8 minus 2 is 6. 6 times 180 is 600, 1080. Sorry, I didn't think to have a calculator at my side, so this is all mental math. Hopefully I'm getting them right. Okay, so that's really the big takeaway about the sum of the angles, is that you can always find the sum of the angles by finding the number of triangles. Okay, and the number of triangles always just comes from that n minus 2 and multiplying by 180. That's what I really wanted you to see in that activity last night. Okay, some examples, some things that you're going to see while you're doing these problems. This says in triangle ABC, the angles are in the ratio 1, 2, 3, respectively. Okay, so that means whatever your smallest angle is, the next angle, the next biggest angle is going to be 2 times as much as that one is, and the next biggest angle is going to be 3 times as much as that one is. That doesn't mean that 1, 2, and 3 are your actual angle measures, but that just tells you what their relationship is, that you're going to have one angle, and then another one that's twice as much as that original one, and then another angle that's 3 times as much as that original one. So here's how I would think about this. My smallest angle I'm going to call x, because I don't know what it is. My next biggest angle then would be 2x, and my next biggest angle would be 3x. And this is a triangle. What do I know about the degrees in a triangle? They have to add up to 180. So I would write this out as, x plus 2x plus 3x has to equal 180, because I know there's 180 degrees in a triangle. So when I combine these, let's see, 1x plus 2x plus 3x, that gives me 6x equals 180. Divide by 6, and x equals 30. So that's one of my angles, my smallest angle. So this goes with that 1. Okay, that's my small angle. So my next biggest angle was 2 times x. So 2x would then equal 60, because 2 times 30 is 60. And 3x would equal 90. Now clearly my triangle over there, that's kind of messy. Clearly my triangle over there is not really drawn to scale, but this should be a 30, 60, 90 triangle. And you could double check by making sure that these 3 angle measurements add up to 180, which they do. Okay, so now let's talk about a quadrilateral. The angle measures in a quadrilateral are in the ratio 2, 3, 4, and 6. Find the measure of all 4 angles. Well, really the key to doing example 1 was knowing that the angles in a triangle add up to 180. So now I need to know what the angles in a quadrilateral add up to. And you might already know this, but just in case you didn't, let's follow that process again. It's good practice. So to find what the angle measure should be in a quadrilateral, I'm going to take the number of sides, which is 4, because it's a quadrilateral, minus 2, and multiply by 180. That's really saying 2 times 180, which is 360. So in any quadrilateral, the 4 angles will always add up to 360 degrees. That means in a parallelogram, in a trapezoid, in a square, in just a general quadrilateral, any quadrilateral you run into will always have a sum of 360. So now I can set up my equation using those ratios that they gave me. And this would just be, you could draw a picture if you wanted to, but you don't even need to. It would be 2x plus 3x plus 4x plus 6x. Because I know that whatever this angle is here, whatever this angle, well, there's an angle measure that the smallest angle is 2 times as much as that. Then this angle is 3 times as much as that small angle measure, which is not even one of my angles in my quadrilateral. My next angle would be 4 times as much as that, and my next angle would be 6 times as much as that. So what I'm really looking for is what's my magic number that these are being multiplied by. Okay? Sorry, that was kind of a fumbly explanation. I know it has to equal 360, because that's what I just found. So now let's add up all my x's. That's 9, that's 15x. I'm going to divide by 15. I believe that's 24. I'm right, it's 24. So 24 is sort of my magic number, but I don't have an angle that's actually equal to x. My smallest angle is 2x, so that's not even one of my angle measures. To find my angle measures now, what I'm going to have to go back and do is say, okay, if x is 24, then 2x would be 48, because 2 times 24 is 48. 3x, 72. 4x is 96. And 6x, 144. And now I should be able to take those 4 angle measurements that are in blue, add those together, and those should give you a grand total of 360. I'm just checking in my head real quick. Yep, we're good. Okay, now we're on to regular polygons. So up until now, everything we've done works for any polygon. Now we're talking about what a regular polygon is. And the definition of regular polygon is a polygon with all sides and all angles congruent. Okay, so a polygon with all sides and all angles congruent. We talked about this a little bit when we talked about proofs. I know there were a couple of proofs that we did where we used regular polygons even though you hadn't learned the definition yet. But anytime you know all of the sides and all of the angles are congruent, then you know that it is regular. Now you're familiar with a couple of these already. For example, an equilateral triangle. Well, equilateral means all 3 sides are congruent, and then didn't we learn that in one of these triangles all 3 angles would be 60 degrees? So we would call that regular. Think about all of your quadrilaterals. What's the only shape that has to have all 4 sides congruent and all 4 angles congruent? Well, a rhombus has all 4 sides, and a rectangle has all 4 angles, but the only shape that has both of those is sort of the hybrid of a rhombus and a rectangle, which is a square. So those are the only 2 that really have special names. The rest you would just say regular pentagon, regular hexagon, regular heptagon, depending on the name of the figure. Okay. The regular polygon symmetry theorem, because you know your textbook loves their symmetry, says that every regular polygon has n lines of symmetry. And remember, n always stands for the number of sides that a figure has. Okay? Also important to notice with this is that when I say it has n lines of symmetry, that means that it has what we call n-fold rotational symmetry. We talked about that a little bit with parallelograms the other day. And I'll give you a minute to write this down, and then we'll talk about what that means. Okay, so n-fold rotational symmetry. When you have n lines of symmetry, you can say you have n-fold rotational symmetry. So a hexagon has 6 sides. So a hexagon is going to have 6 lines of symmetry, and it would have 6-fold rotational symmetry. And what that means is, for example, I'm going to use this pentagon down here at the bottom. I've got my 5 lines of symmetry drawn in. 1, 2, 3, 4, 5. And we'll talk about how to locate those lines of symmetry in just a second. But if I held this pentagon down right here in the center and I spun it around that point, I could basically take this top vertex and land it in 5 other positions that would make the pentagon land back on itself. So I could spin it to here, 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 and then I could spin it back to its original position. So I would have spun it 5 times to get it back to its original spot and had 5 landing points along the way. That's called 5-fold rotational symmetry. Okay? Something else you should know about those lines of symmetry. Those lines of symmetry are always angle bisectors at the vertices and perpendicular bisectors of the sides. I'm going to let you jot that down someplace, and then I'll show you in the picture what I mean by that. So if you look at these 2 examples I've given you here, I'm going to look at this line of symmetry number 1 in this hexagon. Notice that this goes right through this side and this side. That line right there is a perpendicular bisector of this side and this side. So that tells me right away, if that's a line of symmetry, that this is a right angle, this is a right angle, and that these 2 pieces are equal and these 2 pieces are equal. Okay? So that line of symmetry is a perpendicular bisector of the sides. There are also lines of symmetry that go from angle to angle. So like if you look at this line number 8, notice this goes from this vertex up to this vertex. Okay? So that goes from angle to angle instead of from side to side. That tells me that this little angle and this little angle would be congruent. I know it's going to be hard to see. And this little angle and this little angle would be congruent, because that line of symmetry is an angle bisector. Okay, let me erase some of those scribbles real quick. Something else I want you to notice in that picture. I've given you 2 different examples. I've given you, and I think I just called this a hexagon a minute ago. I was wrong. This is an octagon. It's got 8 sides. So here n equals 8. Here n equals 5. When you have an even number of sides, your lines of symmetry are always going to go from side to side. So this line of symmetry went from this side across to this side. And you'll see that, like, for example, line 3 does that same thing, line 5 does that same thing, and line 7 does that same thing. But those are the bisectors of the sides. This goes from this side to this side. This one goes from here to here. Okay, so these lines that I just highlighted in red bisect the sides of the figure. So 4 of the lines do that. The other 4 go from angle to angle. Okay, so this line goes from here to here, and it goes from angle to angle. Those are angle bisectors. So line 2, line 4 goes from this angle to this angle. Line 6 goes from this angle to this angle, and line 8 goes from that angle to that angle. Okay, so if you've got an even number of sides, half of your lines of symmetry go from the side to the side. So they go from side of the figure here to side of the figure here. And the other half of the lines go from angle to angle. Okay, so if I give you a 10-sided figure, you can draw in all the lines of symmetry by connecting all of the angles that are across from each other and then connecting all of the sides that are across from each other. Okay? In an odd numbered figure, like the n equals 5, you'll notice that each line goes from an angle to a side. So here, for example, line number 1 starts at this angle, but then it comes down and it's a bisector of this side down here. So it goes from an angle to a side. Okay, angle to a side. If I look at line number 2 starts at a side here, but goes across to an angle. Because in a figure that has an odd number of sides, an angle is always across from a side. In an even number of sides, an angle is always across from an angle, and a side is always across from a side. So line 3 goes from this angle across, to this side. Line 4 goes from this side across to this angle. Line 5 goes from an angle across to a side. So when you're faced with an odd number sides for a figure, start with every corner and then just go to the side that's directly across from it, and that'll be your line of symmetry. Okay? So again, even numbered, the lines of symmetry all go from corner to corner or from side to side because they're across from each other. An odd numbered figure, you're going to go from an angle to the side that's across from it. Hopefully that's clear without all of my crazy hand gestures that I'm doing right now that you can't see. Okay, so 2 more examples to get through and then we're done for today. Find the number of n-fold rotations of a regular heptagon, A, B, C, D, E, F, G. That's just the name of the heptagon. Well, heptagon is how many sides? 7. Okay, so it would have 7-fold rotational symmetry. Okay, and then it says it wants you to actually draw in those lines of symmetry. I'm going to blow this up a little bit so you can see it. So this is an odd number of sides, which means my lines of symmetry are going to start at an angle. Start at an angle and go across to bisect the side. Okay, so there's one line of symmetry. I'm going to go from G across to side CD. There's 2 lines of symmetry. I guess I should be drawing these as lines, huh? Line. I'm going to start at angle F and go across to side BC. Start at angle E and go across to side AB. Start at angle D, go across to side AC. Start at angle C, go across to side GF. And what did I miss? Angle B, go across to side FE. So you should see 7 lines, which remember 7 lines is really 14 arrowheads because every line has an arrowhead on top and bottom. So starting here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which is 1, 2, 3, 4, 5, 6, 7 lines. If I get back to this one, that's the same line I started with. Okay, so 7 lines of symmetry because that was a heptagon, n equals 7. And if you do this correctly, all of your lines of symmetry should meet in the middle and form that center of rotation. Okay, these next questions are really important. You're going to see these a lot. Find the measure of an interior angle of a regular hectagon. Okay, an interior angle, which means I want just one angle measure. Okay? Now, we've talked earlier in this lesson about how to find the sum, how to find the total angle measures. Okay? So if I wanted the total angle measures of an octagon, I would do 8 minus 2, because there's 8 sides in an octagon, times 180, which I believe we found is 1080. Okay, but now I want just one single angle. And the only way you can do that is if this figure is regular, because regular means all of the angles are going to be the same. So you've got 1080 degrees to split up among 8 angles, because if it's an octagon, it's going to have 8 vertices. So you've got 1080 degrees to split up among 8 angles. We're going to take 1080 and divide it by 8. And the number of times I've done this problem, you would think I would know what that equals. 144 is my guess. Nope, I was wrong. 135. Okay, so if I hand you a regular octagon, you could figure out that every angle is going to be 135 degrees, because all of the angles have to be the same, and the total sum needs to be 1080. Okay, if it's simpler for you to start with, think about a triangle. Okay, if I tell you I have an equilateral triangle, which is a regular triangle, okay, and I want to know the angle measure. Well, you know that there's 180 degrees total, and you know that there's 3 angles. So you would have to take that 180, divide it by the 3, and that's how we know that in an equilateral triangle, all 3 of the angles are always 60 degrees. That same process I just did, just with a bigger shape. Okay, let's look at a regular decagon. So my first step is to figure out what the sum would be, how many angles or how many degrees I'm looking at total. So that would be 10 minus 2 times 180. Let's see, that's 800, 640. So that's 1440. Here's where I came up with the 144. Okay, and then a decagon is going to have 10 angles, so I would take that 1440 and divide it by 10 to split up those degrees among all 10 angles, and I would find that every angle in a regular decagon is going to be 144 degrees. Okay, your assignment is out of the textbook. It is out of, I believe, section 6, 7, and 5, 7, but that's totally off the top of my head, so make sure you check. It's on the board in the back of the room, and then I've also left the assignment with the sub. So make sure you get started on that assignment right away. We'll go over it and grade that tomorrow. Have a great night.